Howdy.
Great. And today we have Dr. Silford and from University of Michigan. And he is actually nationally and internationally well known actually as a math educator, and has been doing a lot of wonderful work and mathematical problem solving, thinking, assessment, and also address achievement disparity issue, and had kind of over $10 million grant before also doing something like called PISA. That back in more than 10 years ago. So fortunately, today we have him to come to share with us some things he's doing and help us put us front, about this research in math education. Another thing I want to share with you is he actually was and still is my advisor. So I'm so lucky today now I've become a student again. So I'm very happy. Welcome.
Thank you. Thank you. It's a pleasure to be here, and I will. I'm happy that those of you who are students of Professor Lee now can be my grandchildren, I guess, or something. I hope that's okay. Anyway, I'm really delighted. This is my first trip to Texas A&M, and is it traditional to start some event with a howdy?
Always.
Always. Okay. Yeah. Okay. That's good to know. So I learned something. That's good. That's good. See, we don't do that in Michigan, but that's good to know. So thanks for coming. You look like students. Mm-hmm. Okay. Yeah. Okay. Most of you look like students. Okay. Undergraduates. Yeah. Some graduate students. Okay. Okay. So. How many of you know what PISA is? Not pizza. And not the Leaning Tower, but PISA as an international assessment. Yes? That's all I know. That's all you know. Okay. All right. Well, then I will spend some time talking about what PISA is, because I think it's, I of course would like to talk about my own work, and I have no controlling interest. I make no money from PISA. I have no vested interest in PISA. I'm just an observer and a fan of PISA as an assessment. Most of the time in the United States, people know about TIMS because TIMS has been around longer. It's an older assessment. The International Mathematics and Science Study is what that now stands for. There used to be a first International Math and Science Study, and then there was a second, and there was a third, and after the third they decided to go back to keep TIMS as the acronym and just call it the International Study. Anyway, most people in the U.S. know about TIMS, and in part that's because the U.S. Federal government has spent a lot of money supporting TIMS. And so because we spend a lot of money on it, we make sure everybody knows about it. And so people are pretty familiar with the results of TIMS, and that's a very good assessment. PISA is another international assessment that is quite different from TIMS in some ways. It's similar to TIMS in that it's international in scope and that it tests mathematics and science, but it's also different in other ways, and I'll try to illustrate that with my talk. And so the title of the talk has in it this notion of looking beyond the headline. So what I'm going to do is provide some overview of PISA, give some examples and results from PISA. Then in the time that's left, I will talk a little bit about some work that I've done in an NSF-supported project called Update, and some of the ways in which that work has been used with teachers in Michigan. Okay, so I have many more slides and many more things to say than we have time. So I'll have to make some choices about what to cut. But I do think it's worthwhile, especially since most of you don't know much about PISA, to learn a little bit about it. So beyond the headlines was part of the title. So recently there was the results of the 2012 PISA assessment were recently released, and I just picked out two headlines, one from the Christian Science Monitor and one from the Atlantic. So we got we have a conservative media outlet and a liberal media outlet, and so we have fair and balanced presentation here. And you can see the kind of headlines that, these are actually very ambitious headlines. These headlines actually kind of have a little bit of content in them, but they basically tell the same story that almost every headline tells about American math education, which is, it's not very good. So PISA has fed into that, and it's got a lot of attention in the 2012 release because it started getting a lot more attention in 2009, as I will show you in a second. But it actually has been getting attention a little bit. It's just kind of a tiny blip in the newspaper. So USA Today announced in 2004, when the 2003 results were announced, that we had weak practical skills, and then apparently we did even worse or something, I don't know. But you know how the headline writers just do this. But these later headlines show a little bit more information, they show a little bit more engagement. So there has been a growing interest in PISA, but mostly it's been to announce more bad news and doom and gloom about mathematics education. The big event, the big moment for the US in PISA came in 2009. When the 2009 results were announced, there was, you got these kinds of things. Arne Duncan, who's the Secretary of Education, announced that the 2009 results were a wake-up call. Barack Obama called it a Sputnik moment. Anybody know what that means? You all know what that means? No, maybe not? Yes, okay. Anyway, back in the days of what was called the new math, when Russia launched a satellite into space and actually kept it up there for a while, it was the Russian word for satellite was Sputnik, and that's the word that caught on in the U.S. and that led to a tremendous federal investment in mathematics and science and engineering. So Checker Finn, who was a Department of Education leader at a previous administration, called it parallel to Pearl Harbor Day in 2010, because the results were released on December 7th, and that somehow it was we were attacked by China, because in fact what happened in 2009 is that the top performing country in math, science, and reading was Shanghai, China. Okay, so it wasn't a country, it was a part of a country, but Shanghai was all of a sudden, for the first time, involved in PISA, and not only did they participate, but they won the horse race, and they were the highest performing country. So that got a lot of attention because it was China. So I'd just like to point out that if you look among the high performing countries, there's a bunch that you probably would expect. We're used to Southeast Asian countries doing very well, so the top performing countries are all Asian countries. Maybe you've heard about Finland and the so-called Finnish miracle. Finland has done very well in PISA, and this is the place where they've gotten all that attention. Liechtenstein's a tiny little country, Switzerland, Japan, another Asian country, and then there's Canada. And I just want to point out Canada because I became very interested in Canada and its performance in PISA quite accidentally. I happened to be visiting Taiwan, and I was giving lectures at several universities, and I was near the end of my trip, and I was supposed to meet with a man named Fu Lai Lin, who happens to be a very prominent mathematics education professor in Taiwan, and we were meeting in Taipei, and he called me the day before our meeting was scheduled, and he said, "I'm really sorry, I'm not able to meet with you tomorrow as we planned, because the PISA results," this was for 2006 results, "are being released tomorrow, and Taiwan is #1 in the world in mathematics, and I have to go to this press conference and explain why people shouldn't get too excited about that." So he said, so I'm not going to be able to meet with you because I have to go to this press conference. And then as an afterthought, he said, you wouldn't want to come, would you? And I said, sure. I've never gone, for one thing, I've never gone to a Chinese press conference, but I've never gone to a press conference where there was good news being announced about mathematics. I've been to press conferences, but never about good news in mathematics. So anyway, so I went to this press conference, and of course, because my Chinese is very limited, I could spend a lot of time looking at the graphics and looking at information that I could comprehend. And one of the things I noticed that was very interesting was that Canada was a high-performing country. And that interested me a great deal because while I think it is interesting, and it's interesting to the Taiwanese, they want to compete with Singapore and South Korea and Japan and mainland China certainly. But for us, you know, I'm thinking Canada. Why would Canada be so good? We have so much in common with Canada. How come Canada can do well on this assessment? So I thought, well, maybe it's a fluke. You know, maybe it turns out the 2006 results were just an accident. And so I came back and started digging into this more, and as I'll mention, it's become a bit of an obsession of mine. But I do think there's a lot we could learn by paying attention to what's happening in Canada. Okay, so PISA. So it's an international large-scale assessment organized by the Organization of Economic Cooperation and Development, which is a European organization centered. It was in Paris. I think it's in Switzerland now. I can't remember. It's a member organization. Many countries in the world belong to OECD, and OECD has relationships with a larger number of countries. It's basically an economic organization, and the National Center for Education Statistics in the U.S. coordinates it. The goal here, and this is really what's different about PISA, and I think very interesting as compared with TIMSS. So what PISA is about is what they call policy-relevant data on the yield of education systems. So what they want to know is how well can students nearing the end of compulsory schooling apply their knowledge to real-life situations. So they're not asking how well kids have learned the curriculum that they're taught in school and whether or not we can find topics that we agree across the world. Everybody teaches this topic, and then how do students do on the topic that we know was taught or we expected them to learn in the curriculum. But they're saying, so kids go to school and then they leave school. And it turns out that when they started this process of developing PISA, 15 years old was the age at which the majority of the OECD countries was the end of compulsory schooling. So you didn't need to go to school beyond that. It's now a little bit higher than that, the age, but that was where they started. So they assess 15-year-olds, and they're asking the question, what do 15-year-olds know that they can actually use? If we give them reasonable problems to solve, can they solve them? So that's really important, and that's, I think, what makes this interesting, is that it's not strictly a test of school knowledge, but it's a test of, can you use something that you probably should have learned in school that might be useful to you to solve this problem? Okay. So there's sizable country samples, 15-year-olds, there's tests and questionnaires for principals, and it's administered every 3 years, and they started in 2000. Okay, in 2012 there were 65 participating education systems, and they use the term education system so it covers things like Hong Kong, Shanghai, that are not countries. They claim roughly 90% of the world economy. Remember, it's an economic organization. So it's a sizable chunk of the world that participates in economic affairs. In 2012, what was interesting was that 3 states in the United States, Florida, Massachusetts, and Connecticut, each participated with a high enough level of participation, with a sample that was drawn appropriately, so that they could be treated as if they were a country. So there was a part of those states that were also included in the U.S. national sample, and then they also participated as if they were a country. And this has been done in some other international assessments as well. Okay, so what PISA tests, 3 different subject areas: mathematics, science and reading literacy. And what they do is they test each of those 3 areas in every assessment, which is every 3 years. But then they rotate in one assessment. One of those areas will be the major area, and it gets about half of the testing attention, and then the other 2 areas split the other half. So in 2003 and 2012, math was the major area. In 2000, it was reading literacy, then 2009 again, so science. Also in 2012, they had a computer-based math and reading literacy assessment, and then they're experimenting. Again, this is an economic organization. They're experimenting with something called financial literacy. Those results will be released sometime this year, and you will probably see newspaper headlines about how U.S. students, can't balance a checkbook or something, whatever the results of this will be. And they also have a problem-solving assessment, which is computer-based. There's average scores are reported. That's mostly what gets reported in the newspaper, although sometimes things called proficiency levels. They basically divide the world up into, I'll show you this in a second, 6 different levels of performance, and then report the percentages of students who score each level. So you can see the high performers. Every country has some students performing at a high level, some students performing at a low level, and the distribution across the 6 levels is something that's also of interest. What I guess I would say about PISA, I guess people would say this about TIMS too, but it certainly is true of PISA, is that its main intent is not to compare countries, even though that's what typically gets done in the media headlines, right? Is the U.S. finished here compared to other countries? That's not its main point. Its main point is to try to give you information that would be policy relevant, so you could say, are we getting enough for our money out of our system, and how can we tweak it so that we get more of what we want, right? And so it tries to provide other kinds of data that might be helpful. And there are a variety of subscores. Gender is looked at across the world, and language spoken at home is looked at across the world. Race and ethnicity are not looked at across the world because it's an indicator that the U.S. uses, but a lot of other countries don't use it as a relevant indicator. So you don't have that to compare across countries. Mathematics is conceptualized and in terms of the way in which it's tested in PISA. They think about 3 dimensions. There's a content dimension, which looks at it doesn't talk about algebra, geometry, calculus, number, but you could probably overlay some of those thoughts. Space and shape, change in relationships, quantity, and uncertainty. So uncertainty is more about probability and statistics kinds of items. And then there are processes that have been, now this is the way it was described: reproduction, connections, reflection. Basically you have different kinds of items, some that ask you to reproduce something that you should have learned and know, some that ask you to sort of put 2 things together, and some that ask you to be a little bit more creative in solving the problems. Those are called something different in 2012, and you'll see those in a second. And then everything, pretty much every item, if it's at all possible, is embedded in some kind of situation. Because remember, they're interested in how well you use knowledge in real-life situations. So it has to be situationally embedded. So you don't see a lot of raw math problems. You don't see just naked computation. Here, solve this computation problem. So almost everything is put in some kind of situation. And some of the situations are a little contrived, but a lot of them are very interesting applications. So here's the content categories. Again, it's roughly equally divided across the 4 areas. In terms of the weighting, it may not be equally divided in terms of the numbers of items on the assessment, but the weighting, because students take different, they don't all take exactly the same items, so they weight it to make the scale. So change in relationships is a lot of where you find what we think of as algebra. And so 15-year-olds in the US, the modal grade for 15-year-olds would be 10th grade. And so they're probably in or near the end of a geometry class in a lot of places, if that's or it could be a second semester of algebra in a lot of places, or it could be whatever it is you get in 10th grade. But in most places, it would be one or the other of those. So a lot of what's being tested is some amalgamation of things that have been taught and learned probably in grades 6, 7, 8, 9, and 10. But it's not it's not a 10th grade test. It's across the grades. And this is the language that they use now for the process categories in 2012. Formulate, employ, and interpret. So but basically, you've got 3 levels. You've got 3 things you ask people to do. And some of it's more reproductive, some of it's more creative. And almost all of it's embedded in situations. Here's the proficiency levels that I mentioned. And you can see each one has a description that tells you something about the way, about what is characteristic of items that if you score well on those items, then you have a proficiency, you've reached proficiency level 2 and so on. So there's certain things you expect somebody to be able to do. And this is another thing that you can do. Then you can compare across countries and how well, if you want to do that sort of thing. Or you can compare across time within your own country, how is it that students have done on the assessment over time. Okay, so this is pretty, NAEP, the National Assessment of Educational Progress, also has 2 ways of reporting with average scores and with proficiency levels. Okay, so the tasks are often given in the context of a real life situation. Tasks often have multiple parts. 3 seems to be the modal number. We did get to see unreleased PISA items. I had to go to a windowless room in Washington, D.C. And look at the items after getting permission from numerous people. And I think they must have done an FBI background check or something. But anyway, everything, you're searched and so on. But I got to see some of the unreleased items as well. 3 parts seems to be pretty normal. Because there are released items that I'll mention to you as well. And sometimes you don't get all 3 parts, you only get a piece of the item instead of all of it. It's about twice as many constructive response items as multiple choice items. So there's a lot of student-generated response in this. So students have to write an answer, and many of those answers require some kind of explanation of process or justification of an answer. On the paper and pencil test, it varies by school. If in the school kids use calculators, if that's the normal practice, then they can use calculators on the test. If they don't use calculators, then they don't use calculators on the test. So it's basically a school level decision as to what's done as far as calculators are concerned and other tools. There's no accommodations, but sometimes students are eliminated from the eligibility pool. So if students are severely cognitively impaired, then they wouldn't be in the random sample. 2 hours for the total test and partial credit. All right, so here's some examples. So here's an example of a PISA item. This one is, as I said, typical of, this is a released item. Ning from Singapore, preparing to go to South Africa for 3 months as an exchange student. She needed to exchange some Singapore dollars for South African rand. So then you get this scenario where you know what the exchange rate is, and then she has this many Singapore dollars and then how many dollars. And this simplifies the situation. There's no commission fee for the person doing the exchange. There's no cost to this exchange. You're simply doing this as a straight proportional problem. So, and over here you see the OECD performance. About 80% got it right. this item across all the OECD sample, and then in Canada it was 86%, in the US it's 54%. So that's a pretty straightforward proportion problem that students scored well below the international average. Then you go to 12.2, the second question. Now she's going back to Singapore, and she's going to exchange with the money she has left back into Singapore dollars, but the exchange rate has changed. So now you have to do this conversion back, and so how many Singapore dollars does she get? All right, so again, it's the same idea, but now it's got a little twist. Here, interestingly enough, the U.S. students did better than they did in the first problem, even though in the other samples that I mentioned here, OECD average in Canada, students do a little worse. But U.S. students did better on this one, interestingly enough. Well, there's some good news. How about that? We could make a headline out of that, right? U.S. students know how to translate, how to translate South African rand back to Singapore dollars. A very valuable life skill. Anyway, and then, as is typical of PISA questions, the third question is, I think, the kind of question that. So the first two questions are not that unusual. You might find those in any textbook. That it may have a slightly different. It might not be South Africa and Singapore, and it may not be Mei Ling, but you might find it in any textbook for junior high school students, right? But the third question is interesting. It sort of says, okay, so during that 3 months, the exchange rate changed. So what? Is that in her favor or not in her favor? So it's asking a different kind of question that requires students to think, okay, would she have been better off if the exchange rate had stayed the same? Did she make more money? Did she lose money because the exchange rates changed and so on? So it's asking for more reasoning, and that requires some explanation and justification. And here you see that not only in the U.S. but everywhere, the success rate goes down. I mean, this is a more challenging item, and you have to provide a good explanation, or else you don't get credit for it in the scoring. And so that's one example of a PISA item. You can see this is pretty much junior high school work. This is not 10th grade, but these are 15-year-olds. But this is the sort of thing that you could argue is the kind of thing you'd expect students who graduate from school, they finish school, they ought to be able to do this. Okay, then here's another one. A lot of PISA items are presented with graphical information. They're very fond of using graphs and tables, tabular displays of various kinds to present information. Here's a task that compares males and females in the Netherlands in 1998. Okay, so here you have these are the ratings for males and females who are between the ages of 10 and 20, and you have a curve for the males in 1998, the average height, and the average height of the females in 1998. And I bet you can already imagine what some of these questions are, right? And in another thing I like to do, I would like to present a situation like this and just ask you to make up problems from it, right? And you could do that. You could make some interesting problems. And it turns out that PISA does most of the things, asks most of the questions that I think you would probably be inclined to ask. First question that they ask, this is another three-part one. This one is interesting for reasons that are not so interesting, I guess, but it is mildly interesting anyway. This one, they tell you that the height of 20-year-olds has increased by 2.3% to 170.6. Now, you don't really know that it's 170.6 on the graph because you can't see it that precisely, but you know it's a little bit more than 170 on the graph, or it looks like it probably is. What's the average height of a female in 1980? So you don't need the graph at all for this, right? You can just do this. It's just an arithmetic problem and dressed up in a context. you can think it's related to the graph only in the sense that it's consistent with the information that's presented in the graph. So here you find pretty good performance, but not outstanding. I mean, it's not overwhelming performance. 2/3 of the kids in Canada, a little more than half the kids in the U.S. Korea has 81% on this argument, for what it's worth. Now, then you get to the graph. During which period of their life are females taller than males of the same age? Okay, so if you remember the graph, there was a little section of the graph over here where females were taller than males, right? So that's what you're supposed to pay attention to answer that question, and then you get this kind of result, which again, it seems low to me. I expected that this is not that difficult, and that I expected the numbers to be higher, but roughly 50% worldwide, a little more than that in Canada, less than that in the US, 80%. Korea. Okay, so those are two pretty routine, straightforward. Then you get this third one. Explain how the graph shows that on average the growth rate for girls slows down after 12 years of age. So now you go back to the graph and you realize that you look at that now and you can see, you'd have to think about how the graph starts flattening out at 12. And so there's something there that's about slope and rate of change and anticipating some of those ideas. And something that is a cogent explanation of that is necessary in order to get full credit. And students did okay on this. Again, roughly 50%. Not a big drop-off in performance on the third question here. And Finland was the highest. So the Korean students apparently did well as well. Then this is one of my favorite tests. This is also a 3-part test. This is the apples test, and I'm going to come back to this one again if there's time later and show you what we did with this, because this is one of the tests we've used several times with teachers. This task shows a pattern. This is kind of a convoluted context, but nevertheless it's an interesting problem. This shows a pattern of planting apple trees. So the dots here are apple trees, and the X's are conifer trees that surround the apple trees. Okay, so this guy's got an orchard, plants them this way, and you're supposed to generalize this pattern. Right? That's the idea. And so the first question is fill in a table, probably what you would expect, for the number of conifer trees, for the number of apple trees, for the number of, for any number of rows of apple trees. Okay? So, and there's a number of rows of apple trees. That's how we did on that. U.S. students did better than the OECD average, which doesn't happen very often. But American students, again, in middle school, probably get a lot of experience doing that kind of pattern, filling in tables and identifying patterns and so on. And so they did pretty well on that. The next question starts to get a little bit more algebraic. It says, okay, so suppose the number of apple trees is n squared, number of conifer trees is 8n. Where's the, now what's a value of n for which the number of apple trees equals the number of conifer trees? Okay, and then show how to calculate it. Okay, so they are. This is what happens to be a question where they actually wanted you to give both answers, and then they gave partial credit if you only answered 8. One of them. You didn't give 0 answer. So they can do partial credit. Performance was a big drop-off here. About a quarter of the kids got this everywhere, a little bit higher in Canada. And Korea did quite well. Then the third question, again, when you get the third question, it's going to be more interesting. Third question says, so the farmer wants to make a much bigger orchard, many rows of trees. As he makes the orchard bigger, which will increase more quickly, the number of apple trees or the number of conifer trees. So now you're talking about rate of change, rate of growth, and you're starting to anticipate something that's a lot more sophisticated than this. And here, again, you have to explain your answer, right? And here, you know, there's a big drop-off in performance internationally and in the U.S. So, but the question, you know, again, has a kind of arithmetic portion, algebraic portion, and then something that's kind of, well, algebraic, kind of pre-calculus almost portion, right? And very interesting. All right, so Professor Lee has all these slides, by the way, if you want them. But there are sources you can get. There are more PISA tests now. When we started my NSF project, there were 50 math tests that have been released. There are more that have been released since then. And if you're interested, there are sites. You just Google it, you know, PISA mathematics, and you can find all kinds of things. But at OECD's website, there's a PISA site associated with the Australian Centre for Education Research. They do a lot of work for PISA. And then the U.S. government, the National Center for Education Statistics, has a lovely display now of PISA stuff. It happened, all this happened after 2009 when we got this wake-up call from Singapore. So thank you for joining, because now we've got a little bit more attention to PISA. Okay, so 2009, as I said, was a big year. If you just look at the countries that belong to the OECD, that's this group right here. We were sort of in the middle of the pack. 17 countries higher, 5 lower, 11 not appreciably different. We were at the low end of the middle of the pack, I guess you could say. That's just average score. Then if you look at all the participants, you end up seeing that there's more. There are other countries that aren't officially members of the OECD that participated, and other education systems. So Singapore, Hong Kong, Shanghai, and so on participated, and Liechtenstein, and so on. And only Latvia, I guess, was in our performance group, and then a bunch of other countries that were also members. So this is the kind of information you get from PISA reports that you can see, and you can see where we sit. That's one kind of information. Then you can look at what's the trend been. I mean, how have we done compared to previous years? And so our score was up in 2009 compared to 2006. So there was actually a little bit of good news. Our higher score was higher than 2006, but not measurably different from 2003. So it's good news, but not great news. It's not like we're really doing a whole lot better. And we were, continue to be lower than the OECD average. And so you get that kind of information, trend information. In 2012 rather, we ranked better in reading than we did in math or science. We were below OECD only in mathematics. So in science and reading, we were not below, not measured, not statistically below the OECD average, only in mathematics. Again, we had poor performance in mathematics in terms of proficiency level performance, and our top performers were lower than top performers in other countries, also in mathematics. And there was no measurable change over time. There is a difference in score. Our score went down. The OECD average score went down. Canada's score went down, and Shanghai score went up. And so there were some changes, but statistically, these aren't all statistically significant. So there we are below the OECD average. See, we're in a different performance cluster in mathematics literacy. And again, so what happened in 2012, Canada didn't do as well, and they actually got upset about it. And what they decided to do is that they needed to spend a lot more money on teacher professional development to help teachers do a better job. So I thought that was a sensible response, different than what we do. All right. So then, if you look at where the states did, remember there were 3 states that participated. So Massachusetts And Connecticut would have been high-performing countries if they had been included in the country level. The Massachusetts was higher than the U.S., and Massachusetts was higher than the OECD average. Connecticut was higher than the U.S., but not OECD. And Florida was lower than both OECD and the U.S. So that gives you a sense that there's variation across states in the country. There's going to be variation within states as well, of course. And those are the only 3 states that we have the information for in 2012. And 2012, the math performance in 2012 is actually really worth paying attention to, more so even than 2009 or 2006, because it was the year when math was the primary area. So you have a much better test of mathematics, you have more math items. U.S. students do, the OECD average on quantity and on space and shape are higher than the U.S. So we do worse on things that have to do with number and things that have to do with geometry and measurement. The geometry and measurement has been a classic area where we have underperformed compared to the rest of the world. The U.S. has consistently underperformed in geometry and measurement. In probability, the uncertainty in data, and in change in relationships, there's no significant difference. Although our score is lower, it's not statistically significantly lower than the OECD average. Okay. Yeah, so this is an example of what you might see in a report about proficiency levels. So proficiency level 5 or above, 5 or 6, there's 6 proficiency levels, and so this is pretty good, high levels of proficiency, and you can see that the U.S. is in this second performance block again in terms of students who perform at a high level. And then you can see also, as the next slide will show, if you look at the below level 2, we have a considerable group of students who are at below level 2. So we have smaller than we would like group of top students and a larger than we would like group of bottom students. And that's and in both cases significantly inferior to the OECD average. And then this is looking at the what it took to get in the 90th percentile, and what it took to be in the 75th percentile, and so on. And in mathematics, there's been no measurable change since 2003. So, although there's fluctuation, it's not statistically significant. Well, these are all results. These are the kinds of things you'll find if you look at a report from the National Center of Education Statistics. You'll find analyses like this. This is anyway. So some countries go up, they go down. There is variation. The U.S. is not. We're very focused on the U.S., but other countries move around as well. So you do see fluctuation in scores. In and of itself, if all we had were these reports from the National Center for Education Statistics, we would have something that might be worthwhile, but it wouldn't be really very helpful in terms of trying to figure out what would we do to make it better. How would we improve anything? So what Project Update was about was based on this proposition that I thought we could use information from PISA, and information meant tasks, and it meant student data, and it meant information of the sort that in ways that we could promote improvements, enhance teacher education or teaching on the part of mathematics teachers at the middle grades and high school. So the intent of the project was to explore the feasibility of using PISA items and data to enhance the work of teachers, and partnered with a school district that is I don't know if you have those kind of things, but it's like a regional school district. It's an umbrella over independent school districts in the state of Michigan, in Oakland County, and I've done a number of projects with the folks there, and they're great partners, and so they agreed to help out with this as well. And we also used in teacher preparation studies at the University of Michigan. Okay, so we paid attention to three things in particular: algebra, quantitative literacy, and equity. Those were the three areas. I'm not going to say a lot about each of these, but we tried to think about what there was in PISA that might be usable and useful. And we picked these three because algebra was an area that we thought was a very commonly taught, very commonly understood area of attention in the mathematics curriculum. So teachers knew they were responsible for teaching this, kids were responsible for learning it, and so on. But the way PISA assesses algebra through this change in relationships approach and so on was a little bit different. The kind of questions, like that apples task question, is not a typical algebra task, right? So there would be something in engaging with that task and thinking about it that teachers might learn and think harder about. Quantitative literacy, I mean, you could argue that everything about PISA is about quantitative literacy, but the quantitative literacy is a topic that's been talked about a fair amount in mathematics education. There are people who have advocated for a quantitative literacy sort of approach to teaching basic mathematics courses at the college level, also at the high school level. It's very much grows out of a spirit that is, I think, compatible with PISA's intent to ask the question, what is it that students can do with the knowledge that they learn? So if you're reading the newspaper, can you understand what you're reading in the newspaper when it has quantitative information associated with it? Can you do basic mathematics in a way that can be applied to situations? When there's arguments about public policy issues, healthcare, energy costs, whatever it is, can you use the mathematics that you've learned or the science that you've learned in order to participate in some intelligent way in that kind of conversation? Quantitative literacy is what that's about. Now, math teachers don't think they teach quantitative literacy generally, but if you show people tasks that you classify as quantitative literacy tasks, they think students should be able to do them. So, and they tend to involve something mathematical, but they're not necessarily the explicit focus of many of curriculum. So quantitative literacy is another area that we thought would be interesting to explore. And equity, we got very interested in this Canadian thing. And I won't spend a lot of time on it, but Canada is very much like the United States. We share a lot of common history. We share a dominant common language, and there's a large portion of the population that speaks another language. In their case, it's French. In our case, it's Spanish. We have a history of having treated indigenous people not very well. We have a common. The National Council of Teachers of Mathematics is the same organization for Canadian teachers and for U.S. teachers. We breathe the same air. We share a lot of similarity. We are much more like Canada than we are like Finland or Liechtenstein or Shanghai or Finland. So we have a lot of cultural similarities to Canada, but Canada has, well, I'll show you. Okay. So although algebra is not used to characterize PISA tests, there's lots of algebra in the assessment items. We identified roughly a third of the items that we that were released that we thought had something that was could be thought of as related to algebra content in some non-trivial way. The quantitative literacy, very much engaged in much of PISA. Interpreting data, logical reasoning skills, practical knowledge, that sort of thing, which are topics that have been identified by Lindstein and others as being at the heart of quantitative literacy. And roughly a third of the tests were clearly about that. And then there's the equity dimension. So there's a bunch of different ways you can come at equity in PISA. There are good data in PISA. Well, there's data in PISA. I don't know how good it is actually, but on family socioeconomic status that is inferred from responses both on the principal questionnaire and the student's questionnaire. There are inferences made about student and school SES. And then there's gender identification, so all over the world. So you can look at gender differences, you can look at differences due to socioeconomic status. There is a significant difference between high SES and low SES students all over the world, and the OECD average. That difference varies considerably. The US is about as diverse as OECD is. We tend to pile up a little bit more at the low end, so where there is something to look at in terms of SES variation, and occasionally you'll find male-female differences. There is an overall difference in the OECD on several of the assessments. There has been a difference favoring males in mathematics, which doesn't happen in the U.S. results usually, but does happen overall in the OECD results. So those who are interested in that. Then there's the other thing that's really interesting, and I have one slide that's misbehaving, so I can't show you the part that I think is really special about this. But we got very interested in this. Here's the United States. So what this shows is the proportion of variance in performance within schools. So this is the variation between top performers and low performers within schools in the U.S. So it's a substantial variation within schools in the U.S. Not the highest of all the countries, but substantial. And then there is also a variation between schools. So it matters which school you go to, right? So there's an analysis that's done that tries to parse out the variation in performance that is within school variance and the variation in performance that's between school variance. Okay. Then if you look at Canada is over here. So what you see with Canada is a somewhat lower than the U.S. Variation in between school, within school differences, although there's a substantial variation within schools. Some students do better than others. Some students do better in math than others within school. But a much smaller variation between schools. So the between school variation is the one that a lot of people interested in equity care about, because there are folks who say that you can predict in the United States, you can predict a student's achievement on the basis of their zip code, and basically, you can, if they go to those schools in that location, then they're probably not going to do very well, and whether it's the school or whether it's the students or what it is, whether it's the social organization of opportunity, it is a fairly reliable finding that there's a lot of variation between schools, more variation between schools in the U.S. than in Canada, about twice as much. And in the U.S., most of that variation is highly related to SES differences. So you do find that the variation between schools is highly intercorrelated with that's the slide that's not behaving, so I can't show it to you. There's a substantial portion of that yellow bar in the U.S. that is, I think it's the doctor there, in Canada, it's less than half the bar. So there's something else going on. And Canada actually has publicly supported private schools, and they have a number of different things that are slightly different than the U.S. Their Catholic schools receive state funding. And there's a number of ways in which they're a little bit different. But anyway, so what this allows you to look at, though, is there are a number of equity-related issues, and what we tried to do in the project is we tried to take data from PISA that would help us unpack this, because what Canada has, that I don't have a good slide to show you, is Canada has, as I did show you already, high overall performance. That is, they're in the top group of performers in math and in reading and in science, and relatively smaller variations due to SES. So they're providing more equitable educational opportunities, getting more equitable educational outcomes for students than is the case in the United States. And they're not the most equitable. It's not the best story, but it's the best story that's like us. It's the best story that's almost identical to us in so many ways that you'd say, if they can do it, then how come we can't do it? And so we should be able to do it, I think. Anyway, but unfortunately, PISA doesn't have great within-school measures. It doesn't have really good measures of classroom practice or anything about the curriculum. So we don't know what kinds of variations there might be in teaching practice or curriculum that might be contributing to this. We do know some things about the social surround of education in Canada, and we looked at that. But what we did with mathematics tests, and I'm going to spend just a little bit of time on this, and then I'll try to leave time for questions. So this was I'm going to give you one example of a project that the folks at Oakland Schools, and I worked with them, they called, the overall project was called Delta, Developing Excellence in Learning and Teaching Algebra. It was composed of it was a big initiative across the different independent school districts within Oakland County that had a number of different components. There were a number of different things that they did. They had content courses for teachers that teachers could take if they needed content. They had various kinds of enrichment. They had a technology-based program. They had training for coaches. They had a lot of different components, and school districts and individuals could sign up for whatever pieces of it they wanted. And in one of those pieces, we used some of the PISA materials that Update had been working on. So the component of the project I'm going to talk about is this one that was about, it had a funny name, but anyway, it's about increasing curricular connections and coherence. So the idea was, these were teachers from grades 6 to 10, basically. I think there were some 11th grade teachers in there as well. And the issue was, how do we get the algebra that we want students to learn taught efficiently and effectively across those grades? Because what the professional development specialists at Oakland County thought was that there was a lot of duplication of effort. That is, teachers at the higher grades were assuming that kids didn't know anything because sometimes they didn't know how to do it exactly the way that they wanted them to do it. They didn't know the formalism. They didn't know the way in which it should look in ninth grade, whatever, in the formal algebra course. And so they started to teach it all over again. And that wasn't very efficient. Sometimes students were given the same problems to solve multiple years. And sometimes the teachers in the lower grades didn't understand well enough what it was that they were supposed to be getting students to learn out of what they were teaching them, so that they'd be able to do a better job at the later grades. So the idea of building coherence across the grades is really a challenging one, and it's one that is not a trivial matter, because people are very, the folks in the project were very well-intentioned teachers. They worked hard. They were good teachers. They were very focused on what they taught. They knew their content at their grade level, and they knew how to teach it. And they didn't know a whole lot about what was going on in earlier grades, especially when you cross school boundaries, like you go from high school to middle school and so on. So the folks at Oakland talked about increasing coherence and connections at two levels. One was the systems level, that is, across each of these districts, across the grades. How do we make things more coherent? How do we build better connections, stronger connections? Basically, how do we support this crossing boundaries from grade to grade, school to school? And then the other was within the classroom, within an individual teacher's classroom. How do you build more coherence and connectivity in the mathematics that you're teaching when you're teaching students about algebraic ideas? So there was a lot of focus on those things: task selection, identifying misconceptions, connecting the part. Okay, so we came up with an idea that we called anchor tasks. And anchor tasks were tasks that could be used with students at multiple grade levels, and where they could legitimately be thought of as a task that you could hand a 10th grade student to solve, or you could hand a 6th grade student to solve. But you might have different expectations about what you're going to get from the students at the different grade levels. So they had to be, and what the anchor part of this was that what this would allow us to do is to have an anchored conversation involving teachers at different grade levels, because they were all talking about the same task, essentially. And they were talking about a development of expectations and knowledge that you'd expect students to have as they passed through the grades, so that the 10th grade solution wouldn't look like the 6th grade solution. You wouldn't be expecting the same thing. So that was the idea. How do we get these anchor tasks? And then we had something called teaching learning trajectories, which basically were maps of what it was that students were learning. And those started with the state expectations. They then incorporated the Common Core expectations, because in Michigan we were going to adopt the Common Core, and so that's the way it went. It could have been just the state expectations at the time. It could have been anything. But basically you try to say, well, in an ideal world, or the way in which we're supposed to do it, how do you map out the development of these ideas? Every one of these algebraic ideas has some kind of trajectory. There's something you learn in 6th grade, and something you learn maybe in 7th or 8th. And so, okay. So that was the deal. So that's what a trajectory looks like. There's some topic, and that's over here, and then some breakout of grade 7, algebra grade 8, algebra 1, algebra 2. Okay, so you're getting the sense that there's something that's developing over time. Steepness, slope. Okay. So now we come to a task that we use as an anchor task, and this is where the update project and the Delta project merge. This was the Apple task from PISA, except it was modified. And so the modifications were, there was one pretty trivial modification, which anybody who's been paying very close attention can see in this slide.
The type of tree.
Type of tree. What did it say before? Conifer. Well, they were pretty sure, teachers were pretty sure that the kids weren't going to know what conifers were. Right? Now, we live in Michigan, for God's sake. You'd think you know what conifer tree is, right? But anyway, they thought, no, you got to call them pine trees. Okay. All right, fine. So they didn't want the word to get in the way of doing the problem, right? I don't know that it would have, but you always have to worry about the fact that it might be some irrelevant detail like that that would throw somebody off. Okay, so that was the trivial shift. Otherwise, that presentation is exactly the same. And then this question 1 is exactly the same. You fill in the table. And question 2 is not the same. Remember before it said this pattern is n squared, this one is 8n, there's some value from which they are the same, and which one is it, and so This one says describe the pattern in words and symbols, so you can find the number of apple trees at any stage of the pattern. Describe, so you can find the number of pine trees, and then for what values of n will the number of apple trees equal the number of pine trees. Okay, so it's asking for something that is very similar, but it's asking for it in a very different way. This modification was made in order to make it possible for, they thought, for the younger students who wouldn't have as much algebraic facility to solve the problem. And it wouldn't get in the way of the older students, because the high school teachers were quite sure that the high school students would immediately write down 8n, n squared, set it equal. And the only thing they would get confused about is whether 0 was the solution. Okay. So, third question is exactly this. All right, so, we had the teachers work on the problem, they worked on the problem, compare their thinking, they solved the problem, then they talked about what would be an appropriate solution strategy at your grade level, where you teach. You talk to other people who teach at your grade and figure out what do you expect students to do with this problem, and then they created posters where they talked about what they thought, what they expected students would do, right? And then, then what happened is, so between that and this, the teachers went back and in their own classrooms and sometimes in a neighbor's classroom, they got some student work. They got volunteers to give the test. Not every teacher did it. Most of them did. Some of them couldn't figure out how to fit it into their scheme of things, and so it was fine. Anyway, we collected a lot of data. It turns out, unfortunately, that the U.S. does not keep the data that students produce in the PISA assessment. So they score it, and then they destroy it. And we found, with the National Assessment of Educational Progress some years ago, we could go to an underground bunker in Iowa. And down in that bunker, you could find all the papers from the NAEP assessment. And you could find all the wonderful things that students wrote, like a note that says, I really don't have any idea. I hope you have a nice day. Or, things like that, right? That would be very humorous, or they draw pictures for you or whatever, and occasionally there'd be some interesting mathematics in there too. And we were able to use that student work in writing articles for the mathematics teacher, for teaching children mathematics and so on, to illustrate to teachers how the students thought about these problems, and we could use them in workshops, and we could use them. So we thought we'd do the same thing with PISA, and then we learned from the National Center for Education Statistics that they don't keep them. I thought it would all be digitized, and we'd have digital files. We wouldn't even have to go to an underground bunker in Iowa. We could just go to a digital file and we'd have it all, but they don't. They just throw it away. And that's a real shame, because there's so much richness in the responses, and that's really where the action is then. Because then what we did was come back. Well, we did some analysis on the side. That's what graduate students are for. So, they did some analysis of the responses, and then we created these packets that showed different, that had different strategies illustrated in the packets of responses. So then basically you ask people to identify these patterns, and then you said what percentage of students might you expect to use each of these strategies. So these are just selective examples, and so we were getting the teachers to think a little bit about more than right and wrong, which is the first order thinking about it. What's the right solution, the wrong solution, what's a wrong answer and a right answer, and to think more about the way in which students were thinking. All right, so then so they analyzed these sample responses, and then they made predictions about what students would do at the grade levels, and then later on in a subsequent session we showed them how what students actually did in the performance on this test. And so on the second, this is the second item. This is the one with the say in words or symbols what the pattern is, right, for the apples and the pine trees and so on. One of the things that happened that was really quite surprising to the teachers. They did not expect, especially the secondary school teachers, did not expect that we would have so much use of recursion, where students were trying to represent the pattern in terms of how it grew, rather than writing down, you know, the total equals 8n or n squared. Right? They were saying, you know, you add 3 and then you add 5 and then you add 2 more each time to whatever you added the last time. And the thing that was very interesting is that, so recursion was popping up a lot, and especially in the next question, but recursion was popping up a lot. And it was popping up in places that you didn't necessarily expect it. So here's a recursive, this is beyond Algebra 1. These are students who have taken Algebra 1 and they're taking something else now, right? And so the teachers were completely blown away by this. Here's Algebra 1 students using this recursion. The teachers were certain that the students would just write the equations and be done with it. And that's not what was happening. I mean, some students did that, but a lot of students didn't. They fell back on this recursive work. And why that was interesting was in part because what you notice is this hole in the graph at each grade level. Maybe you noticed it. It is there. And that's recursive equations. They didn't have to write down what they were trying, what they were seeing, what they were thinking about, the pattern they found. They didn't know how to express it in any kind of equation form. So they had no notation. They had no functional notation, you know, f of n equals f of n minus 1, something, whatever, or now next, you know, the next one is now plus 3 or something. And none of that. They had no way of representing, because they had never been taught to represent that kind of generalization. So that was a real eye-opener to the teachers. The students are thinking about it this way, and we've left them helpless to write it down in some way. And you see students struggling with language to describe the pattern because you have all these misplaced modifiers. You say, it grows by 3 more than it, you know, and what's it? And it's different in the two, you know, it's like it, or they, or that. It's very awkward. So you need some kind of formalism to express that. Anyway, pretty interesting stuff. The next question, again, here you see a couple of attempts at writing something that we classified as equations, but again, a lot of use of recursion on this, on these tasks. And I think it's not something that shows up in the PISA rubric, because the PISA task, as it appeared originally, didn't invite students to think about it recursively. It basically told them 8n and n squared, so therefore, you know, do something with that. So what you see, because of the transformation of the problem in this transformation to vector task, is that it became a much more interesting task for the teachers to talk about and think about and to ask questions about. Do we want students thinking recursively? If we don't want it, then what are we going to do about it? Because clearly they are. And what's wrong with it anyway? And then how can we move students from thinking about it recursively to the kind of explicit description that or the explicit equation that we would like them to be able to write? We'd like them all to be able to do 8n and n squared and set them equal to each other. So we'd like them to get there. So how do we manage to make that happen? There are some other interesting aspects to this. I would argue that when you think about this problem recursively, you can also get a different answer to part 3 than if you think about it the other way. So it's not like there's it's a somewhat different question depending upon how you ask it. Anyway, so then we went on to ask teachers to think about this. The summary results were really quite different from their initial estimates, both in terms of how students thought about it and what they estimated the use of strategies would be. And that got them thinking about, you know, now what are we going to do about it? Let's examine the curriculum. Let's ask ourselves whether there are opportunities to inject something without having to, you know, change everything without having to start all over again. Let's sort of honor the fact that students are thinking about this and help them to think about it smartly. Because if this is an inclination that they have, then let's try to hone that inclination so that they can actually be adept at using it. And anyway, looking across grade levels, so teachers were thinking both within their own classroom and across grade levels, looking at curriculum materials and identifying the kinds of learning experiences that they might be able to provide. So this is just one example, but the PISA test turned out to be very useful for this kind of anchoring of the conversation because of the way in which PISA draws on content that isn't grade specific. So unlike TIMS would be harder to do that with because the material tends to be much more grade specific, grade placed. And PISA tends to draw more broadly in the full task across multiple grades. So it offers the opportunity, at least, to generate this kind of opportunity. Okay. Representation. All right. I think that's it. I'm going to stop so I can answer questions that you might have. But the project is ending. We're coming to an end. We've identified some tasks that we think are usable for this purpose and for other purposes to provoke thinking about mathematics on the part of teachers, because the PISA tasks, because of their applied nature, because of their contextualization, because of the way in which they blend knowledge from different components of the curriculum, tends to give a kind of richness to the consideration. And this connections and coherence work is one example of where we've used it. We've also used it to introduce prospective teachers to the notion of quantitative literacy and how to be attentive to the skills that students might actually be using in real-world situations, to read bus schedules, to decide how to schedule a Skype conversation with somebody in Germany, given what your daily schedules are like, and how do you decide on the time difference and everything else, how do you decide when you would do that. And, I mean, these are very pragmatic issues, but there's mathematics involved in the analysis of all this. So these are some of the kinds of things that we've been doing. And I think that I just want to leave you with the idea that PISA is a very interesting source of tasks and information that